Okay, today I'm going to solve this validate binary search tree problem in LeetCode. So, given given the root of a binary tree, determine if it is a valid binary search tree, that is BST. A valid BST is defined as follows: the left subtree of a node contains only nodes with key less than the node's key. Okay. The right subtree of a node contains only nodes with key greater than node's key. Both left and right tree must be a binary search tree. That means, let's take a look at this. Okay, if you take this as the current node, the left, the all the values in its left must be smaller than this node, and all the values in the right side must be greater than this value, not equal, greater than. Okay. Similarly, if you take this node, all the values in its left must be smaller than that element, and all the values in its right must be greater than its value. Okay, so in this case, how can we know if it is a binary search tree? The idea here is that we can just check whether the left element is lesser than less than and the right is greater than. If it is not, then we can just say that it is not a binary search tree. Okay, but there is a catch. Okay, if this need to be a binary search tree, all the elements in its right must be greater than. That means in this case this is not a binary search tree because 4 is not greater than 5. Okay, that means this is not a binary search tree. Let's take a look at this. Is this a binary search tree? Let's check. Left element is lesser than the current, right element is lesser than the current, oh sorry, greater than the current. That means this is a binary search tree. So that's the case. Okay, but take a look, the right may become greater than this element. What if the right of this element becomes 10? That means the node 1, the node 1 has a child called 10 in its right. When take the look at when checking on this node, this is a valid binary search tree because the right is greater than the current. But when it takes to this node, on its left, all the element in its left must be lesser than this. So we need to consider that also. Similarly in the right also. Okay, so how can we achieve that? So here what I am going to do is, let's just take a look at the constraints. Here says this is minus 2 is to 31 and 2 plus 2 raised to 31. That means the limit of an integer. Okay. Okay. So the least element we get is this, and the maximum element we get is this. So we can take that. Okay. For now, let's say here max. Let's write this at the time of the code. What we are going to do is we will just take a look at In this case, this is a value between, or we can say, okay, fine. We can say if this value is lesser than this, okay, then return true. And also when we take a look at the next child, we also need to check whether this is less great, this is this row notes right, this is must be greater than this element and must be lesser than this element. That is our case. Similarly in the right, don't take a look at these numbers. If we want to take a look at, if this node is our consideration, this node must be lesser than this node and must be greater than this node because it is on the right. This node's right is this value. Okay, is that make sense? Cool. So how can we achieve that? We can just limit itself. We can say that the value of this node must be less than this value and must not be greater than this value. Similarly, if here a node is available, we can say that the value of this node must be greater than 1 and must not be lesser than 5. Is that make sense? Sorry, I just said that in a wrong way. Here, suppose we have a node here. The value of that is the right of this one. The value of this right must be greater than the value of 1. Okay, and it can't, it would it will never exceeds this 5. That is our case. That means the limit of this value is between 1 and 5. Okay, is that make sense? Yeah. Okay. Similarly, when we take a look at here, the limit of 3, what would be the limit? It must be lesser than this element and must not be greater than this element. That means the value here can be between this. Okay, is that make sense? Yeah, okay. So now let's just code this up. Let's say for now let's call this also return a boolean. Always try to make a new function and make all the calls in that function and return it here. What we can call this? For now let's call it as DFS because we are doing this as a DFS function, and we can pass our root node here, and also what we are going to do, we can get a lower limit and an upper limit. That might be so I'm coding this in Java. You can code it in any language you want. I'm getting an upper limit. So I will talk it about that in later. What would be the base case? What would be the least we get? If we came up here and go to the next, that would be null. So we need to deal that also. What if we get a null? Is that a binary tree? Sorry, binary search tree? Yes, it is a binary search tree. If we get only null, that means it is an empty tree. It also considered as a binary search tree. So let's say if our root is null, that means we can just return true because it is a binary search tree. Now, in each iteration, we need to check where this is available. Is this? Oh, okay. So I need to check where this element. Is this element is contains between the lower limit? This can go only up to 4, and on the maximum value it can go is 5. The lowest value it can go is 4. Don't check the values. The maximum value it can check is 5 because it is not a binary search tree. I'm just taking it as for an example, for a representation. Okay. So we can say if our root current value if it is less than the lower, and also if the current value is greater than the upper. Okay, return false. Why I given that? If the root value is less than the lower and greater than the upper. Otherwise, if when the value is not in this range, we just need to return false because it is not a binary search tree. That I just take a look at here. Yes, we can do it as like this. Sorry, like this. But the problem here is if we code this way, it will much more cleaner. Let me just format this so we can understand that better way. Then in the next case, what we want to return, we just need to check whether the right subtree is valid and the left is also valid. So if right is valid, just need to go to the right. First we can go to the left, and here comes the part. What is the lower? If we want to go from this to this side, what would be the least amount we can get? It can be anything, any value. In this case, this is minus infinity. But what would be the maximum value we can get? That is 5. We can't put a value that is bigger than 5, so that our maximum lower limit would be the same, but the maximum limit would be the current value. That means root dot value. Okay. Also, we need to go to the right also. So root dot right. And in this case, we need to go to the right. What would be the lower least value we can get here? The current value? Yes. Because we can't go smaller than this element. That means it is not a binary search tree. So the lower value is the current value, that is root dot value. What can be the upper value? Anything. So what's the upper? As it is. If any of these returns false, if any of these elements says that it is not a binary search tree, that means our tree is not a binary search tree. So we can put an AND here and just return that. So that let's just format this. Oh, what happened? Okay. Okay. So what here happens is that if both of these are true, then it returns true. Otherwise it returns false. Any of these comes false, then it returns false. Okay. Now what we need to return from here, we just need to return the DFS. What would be the root, current root, and what could be the initial value. I put a integer class. I haven't put the int, primitive int. I just put the non-primitive integer class, because if I put that, I can pass null here. Okay, initially we don't need to check this. Okay, then if we put null, then here we will get an exception, so we need to handle that also. How we can handle that? We can just check whether we are taking lower here, so whether check if lower is not null, and also check here if upper is not null. So it might be so much length, so I'm just taking it to a new line and just take a look. If lower not equal to null, then only check this. Okay, I'm just putting this in this thing so it looks more cleaner. And also we need to check that if upper not equals null, then only we need to check this also. Okay, here we don't need to put and, because we don't even need both to be true. We just need any of these is a binary search tree, then we can just return that. Okay, I think this is it. This may work. Let's take a look and just run this, if this works or not. You can see, okay, we got a wrong answer here. Okay, fine. We are taking the value of root is less than the lower. What happens? The values become the lowest amount, that is this. Then in this case, if we put this values here, by the way, this is a custom test case I have given here for getting this answer wrong. Okay, what happens if this is the maximum limit we can go. Okay, but in this case is this value, if we take a look at this value, if the root value is this, then this value less than this value, if it is true, no, it is equals. So we just need to add this functionality also here, also here also, then it might work, I think. Yeah, it works. Let's just submit that. Yes, it is works. So that's it. I also tried to solve this so much times, but I took me some while to solve this. Yeah, okay, so then okay, bye.